Every day, we experience things that seem to us
random, chaotic, and
unpredictable. From flipping a coin to rolling a dice, playing the lottery, or trying to guess the weather. However,
one of the fundamental assumptions of classical physics is that the laws of nature are deterministic. In other words, if we know absolutely everything there is to know about a system, even a really complex one, then we can, just like clockwork, predict the future of that system.
How can these two things be compatible?
And if we have enough data and the right models,
can we really predict
the unpredictable?
In everyday language, we use the words random and chaotic as if they mean the same thing.
However, in a mathematical sense, chaos refers to systems that are extremely sensitive to changes in their initial conditions. Chaotic systems appear random, but in fact behave according to underlying patterns and rules.
An example? The flip of a coin is used everywhere to help us decide things, because the outcome appears to us completely random. However, when a coin is flipped and caught, we know that it will follow Newton's laws of motion exactly. So there is really nothing random about it at all. In theory, if we have enough information about the weight and momentum of the coin, the wind resistance and other variables, we can predict how it will land every time.
Though we might not be able to predict the outcome of an individual coin flip or dice roll, the law of large numbers tells us that if we carry out such actions many times, the average of the results obtained will get closer and closer to the exact values we'd expect.
Lotteries and casinos rely on this law every day to ensure that, even if gamblers win once or twice, the house always wins eventually.
The odds against winning are so great that the more bets a player makes, the more they will lose, regardless of any clever strategies.
The only way gamblers have ever been able to consistently win at games of chance like roulette is by studying patterns, like the physical movement of the wheel or the deceleration of the ball, and using computers in real time to predict the most likely outcomes. In doing so, they shift the probabilities in the law of large numbers to make winning more likely.
Of course, casinos don't like this, because it means they lose money, and so use a variety of techniques and modifications to ensure their games remain consistently unpredictable. To better understand how the tiniest changes in the initial conditions of a chaotic system can affect its outcomes dramatically, we can use surprisingly simple examples, like a baker kneading dough. As this dough is pressed, folded, turned, pressed, and folded again, the distance between the raisins sprinkled through it increases. As the height of the dough is halved, the horizontal distances between raisins double. If we knead twice, 2 nearby raisins end up 4 times as distant, then 8, 16, 32, and so on. If the starting position of any of our raisins changes even by a millimeter, then the position they end up in will be very different, because the system is exponentially sensitive. Any changes add uncertainty to the system, and that uncertainty is amplified exponentially as we knead our dough.
A defining characteristic of chaotic systems is that due to their underlying order, we can predict the initial outcomes. However, as the effects of tiny changes are amplified exponentially and compounded over time, this breaks down, making longer-term outcomes unpredictable, even with nearly perfect starting information.
With hugely complex systems like the weather, you can understand how tiny changes, like a mistake in measuring the temperature at a weather station, can have dramatic impacts on our predictions.
All matter in the universe, from coins and dice to our oceans and clouds, is made up of microscopic particles. Molecules, atoms, electrons, and other particles whose microscopic dynamics are governed by the fundamental laws of physics.
Characterizing the chaos and randomness of microscopic particles and learning to predict their impact at the macroscopic level is one of the key objectives of our research groups here in Bristol. Like raisins in a bowl of dough, collisions between particles in a gas or fluid show exponential sensitivity to their initial conditions. Just as we can't predict the outcome of a single coin flip or a dice roll, we can't predict the collision of every microscopic particle, but we can again use the law of large numbers and draw on many octillions of collisions to predict what will happen to a gas or fluid at the macroscopic level.
Our latest research has used new techniques in pure mathematics to show how an electron gas travels through a crystal lattice. In doing so, we've predicted a new and unexpected transport phenomenon and solved a puzzle posed by Dutch physicist Hendrik Lorentz more than a century ago. This brings us a step closer to answering one of the biggest unsolved problems in maths, explaining the equations that govern ocean waves and atmospheric conditions from fundamental principles.
The most well-known illustration of chaos theory is, of course, the butterfly effect, conceived by mathematician and meteorologist Edward Lorenz in 1972. It suggests that something as tiny as the flap of a butterfly's wings in Brazil could trigger a tornado in Texas by impacting the initial conditions of the world's weather.
Of course, there are billions and billions of butterflies, as well as many other independent factors underlying a system this complex.
Again, the law of large numbers comes into play, allowing us to predict the probability of a tornado caused by a butterfly. This is extremely unlikely, virtually impossible. You would be more likely to win the lottery 1,000,000 times in a row.
Similarly, we cannot predict exactly what tomorrow's weather will be, but we can make smarter weather forecasts that tell us the probability of specific weather types with improved reliability.
Understanding the mathematical foundations of chaos is important, because this gives us practical insight into the complex systems behind major global challenges and provides the basis for new technological applications.
For example, here at Bristol, our researchers are working closely with the Met Office and using novel approaches such as high-performance computing and machine learning to improve the accuracy and value of weather, climate, and atmospheric models. This takes our fundamental knowledge of mathematics and physics and uses it to improve prediction and decision-making around life-changing extreme weather events such as flooding, storm surges, heat waves, and droughts. Partnerships like this have the potential to be truly innovative,
leading to major benefits for the climate, for individuals,
and for society
as a whole.